This is the last lecture before exam 2. It's section 11.6. We've done most of the work for 11.6. I'm just going to be working some problems and showing you how to find series given other known series and some of the uses of power series. So let's see. These I think we have done in class, and you have seen how each of those series is derived. The first one, of course, let's call that f of x. And we know that that was just the series summation x to the n. And it converges for x in the interval minus 1, 1. We found this series by, well, plugging in minus x into the series. Same thing here. We used function composition. This is f of minus x squared. Plugging that into the series, we get the series for 1 over 1 plus x squared. And arctan, we saw, was the integral of this. So we took the integral of the series for 1 over 1 plus x squared. So I guess I could write this, but you look back in your notes and you will see how we derived each of those series. Now the list on page 595, there's a table of 5 power series, and it also has the series for sine x, cosine x, and e to the x. E to the x we've used several times in problems where it's just given to you as a summation x to the n over n factorial. But sine x and cosine x we haven't worked with yet. For now, you will accept how these series are obtained kind of on faith. And then in 11.7 we will derive those series, and you'll see how to solve for the coefficients of a power series for a function. So keep your book open while we go through this lecture to page 595. And I'm going to give you that table on exam 2. You don't need to memorize these. The first problem, we'd like to find a power series representation for x squared over 1 plus x. So notice that this is a power of x times 1 over 1 plus x. So if we know a series for 1 over 1 plus x, which we do, and it's just powers of x in that series, we can just multiply by x squared easily. So let's see, what was our power series for 1 plus x? Well, if you forget, you can think, oh, well, it is the power series x to the n, but it is minus x plugged in from n equals 0 to infinity. So this is x squared times the sum from n equals 0 to infinity of minus 1 to the n, x to the n. When you're using sigma notation, always get your powers of x by themselves. We don't want to leave it minus x to the n. Well, now you can just bring in your x squared. It's just one big long polynomial, so you multiply it to each power of x, and we would have the sum from n equals 0 to infinity minus 1 to the n, x to the n plus 2. Now in yellow, let me do it another way. You can look back at your power series for 1 plus x and write x squared times, and write out the power series the way they do in the table. They would just write it as 1 minus x plus x squared minus x cubed plus x to the 4th minus, and so on. So you're multiplying x squared to that infinitely long polynomial, and you get our series x squared minus x cubed plus x to the fourth minus x to the fifth plus x to the sixth minus, and so on. So this is exactly the same thing you have here. Notice your first term here would be minus 1 to the 0 is 1, x to the 0 plus 2. First term is x squared. These are exactly the same, and you can use whichever notation you prefer. Something very important here is to remember the interval of notation. I mean the interval of convergence. For x to the n, we have the series converging only on the interval minus 1, 1. And that is true for all of these series that we obtained by using that series. I'm going to do this one all without sigma notation. We're going to start by finding the series for arctan x, and then we'll simply plug 2x into it. So, well, arctan x, we know, is the integral of 1 over 1 plus x squared dx. And 1 over 1 plus x squared is equal to f, if that's our function 1 over 1 minus x, f of minus x squared. So that will be taking this and plugging it into the series summation x to the n, starting with n equals 0. We'll get, well, this to the 0 is 1. This to the 1 is minus x squared. Plus, now squaring it, x to the fourth, minus, now cubing it, x to the sixth, plus x to the eighth, minus, and so on. So that's 1 over 1 plus x squared. That gives us then arctan x as the integral of this. So we'll just integrate term by term. Integrating 1, we get x minus 1/3 x cubed plus 1/5 x to the fifth minus 1/7 x to the seventh plus, and so on. See, all you need to know in these problems is just your power rule. It's easy even for us to integrate these things represented by big long polynomials. Okay, so now all we need is arctan 2x. And this was what we were asked for. So we just plug 2x in for x. So 2x is my first term, minus, and now it's going to be, well, I'm going to take two steps. 1/3 times 2x cubed plus 1/5 times 2x to the fifth minus 1/7 times 2x to the seventh plus, and so on. Now, let's see, I'll choose white here and write our final answer. So arctan 2x is equal to 2x minus, now we're going to have 2 cubed over 3 x cubed plus 2 to the fifth over 5 x to the fifth minus 2 to the seventh over 7 x to the seventh plus, and so on. So that would be the series for arctan 2x. And as we saw, we carefully, last week in class, we saw that the interval of convergence for arctan x, the interval of convergence for arctan x was x in minus 1, 1. Now this time we want 2x. We want 2x to be less than 1 and greater than minus 1. So our interval of convergence changes here. X is less than 1/2 and greater than minus 1/2. So that's important. our interval of convergence changed. I'm going to do this problem again for you, and I will just use the sigma notation. I hope that you'll watch both because I think you learned something from both methods. We first found that the series 1 over 1 plus x squared was f of minus x squared if we are talking about the series that converges to 1 over 1 minus x, which we know very well, the sum from n equals 0 to infinity of x to the n. But I'm going to put in minus x squared to the n, and we get the sum from n equals 0 to infinity minus 1 to the n, x to the 2n. That's our 1 over 1 plus x squared. So arctan x is the integral of this series, the integral of the sum from n equals 0 to infinity minus 1 to the n, x to the 2n dx. We learned in the last section, 11.5, that we can integrate term by term. So really what I'm doing is integrating each one of these, minus 1 to the n, x to the 2n dx. And I think you see that really clearly in the method that we used in the beginning. We just went across and integrated term by term. But we can do that here. The sum from, okay, so let's not put our index down yet. We're going to integrate each one of these. Now remember, we're integrating with respect to x, so this is the exponent that will go up by 1, and we will multiply by the new exponent's reciprocal. So we've still got the constant minus 1 to the n, and we will divide by 2n plus 1, and the power on x will be 2n plus 1. Now, when we integrated, we will still start at n equals 0 to infinity. And now look at this. Let's see if it's the same thing we have in white up there. Oh, I haven't plugged in 2x yet. Excuse me. This is arctan x, and we know that it still converges, if you look back in your notes, for the absolute value of x less than 1. But now we want to get arctan of 2x. So here we plug the 2x in, and we'll get our final answer. I'll put that back in white. And let's see if we get the same thing. Arctan of 2x then is found by plugging 2x into this expression. We get the sum from n equals 0 to infinity minus 1 to the n over 2n plus 1. And now we have 2x to the 2n plus 1. So I'll put 2 to the 2n plus 1 up here, and with the coefficient, and x to the 2n plus 1 here. That's kind of complicated looking, but I think it's exactly what we had up at the top of this slide. Notice when n is equal to 0, we get 1 times 2 over 1. So we have 2x. It's exactly what we have here. And it will be, if you expand out the first 5 terms, you'll see you have the same series. And let's find the interval of convergence. It changes now because we have put 2x into the series. So we want 2x in absolute value to be less than 1. Notice we don't have to use the ratio test for this because we already know the interval of convergence for the summation x to the n. So that gives us again x between 1/2 and minus 1/2. Alright, here's another way that you can use power series. Obviously, for sine x over x as x approaches 0, you have 0 over 0, and you could use L'Hopital's rule much faster. But this is a nice example to show you how you can use a power series to evaluate the limit. So let's write out what our power series for sine x is. And it converges, as you'll see in that table, and we will prove later. Sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, and so on. The sigma notation for that, if you'd like to use it, would be summation n equals 0 to infinity minus 1 to the n, it alternates, over 2n plus 1, odd numbers, factorial, and x raised to that same 2n plus 1. And the series for sine x, you could use your ratio test here and see it converges everywhere, minus infinity to infinity. Okay, so we'll just use this. So this is what's in the table. We'll just write out that long polynomial. Don't forget your dot, 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 because it is a series. Well, now we just want sine x. I change to white. We want sine x over x. Well, that's easy. Just divide each term by x. Subtract 1 from the exponent. 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus, and so on. So there's our series for sine x over x. Now, if you want to take the limit then of sine x over x as x approaches 0, well, look up here. All of these have a numerator of 0. So everything from there on out goes to 0, and the limit is 1. Okay, here's another limit to do using series, not using L'Hopital's rule. So let's see, we need a series representation for that, and then subtracting x will be very easy, and dividing by x squared will just subtract 2 from all the exponents. So let's see, the natural log of 1 plus x, we know that to be the integral of 1 over 1 plus x dx. And we have a series for that. The 1 over 1 plus x was 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th plus dot, dot, dot. So we can integrate that series term by term, and we get x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th plus 1/5 x to the 5th minus dot, dot, dot. So there's our series for natural log 1 plus x. And it will converge on minus 1, 1. Now I want to subtract x and divide by x squared. So I think, well, subtracting x is just, subtracting x just gives us the rest of that series here. So they cross out, and now we want to divide by x squared. And we get, then, dividing by x squared, this will give us natural log 1 plus x minus x, takes off the first term, and now I'm going to divide by x squared. So I'll just subtract 2 from all the exponents. So x to the 0 is 1, and I get minus a half plus 1/3 x minus 1/4 x squared plus 1/5 x cubed minus ... So this is not going to be difficult to take the limit of, is it? If we take the limit, let's see, I've run out of space here, so I'll go back up to the top. If we take the limit of this as x goes to 0, well, all of this part here, the entire series except for the first term, every single term becomes 0. So our limit is, I'll just say, equals -1/2. Well, now we're faced with the same problem that we were faced with almost from the first day of class, that some integrands don't have antiderivatives that we can write in terms of elementary functions, and this was one of them. You cannot integrate this using the fundamental theorem because we don't know an antiderivative. And as you saw, I believe in the last lab, we showed how we could use series to get polynomial estimations of the function and just integrate the polynomial using the fundamental theorem and get a very close approximation. So that's what we're going to do here. I need a series representation for e to the minus x squared. So let's see, e to the x, if you look on your table, I'll put it in summation notation and then into the x to the n over n factorial. So that's equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. And this series converges on the entire real line. And I think we did that in class. In one of your problems, you used the ratio test to see that you got the limit of 0 regardless of x. So this series converges on minus infinity, infinity. Now, a series for e to the minus x squared then will be e to the minus x squared. We're just plugging that in for x, function composition. So in summation notation, you would have minus x squared to the n over n factorial, which is the sum from n equals 0 to infinity, minus 1 to the n x to the 2n over n factorial. Now, you do not need to use a summation notation. Let's say that we're just looking up right here. That's our series for e to the x, and I'll switch colors. You'll know I'm using it. I'm plugging in. I'm going to plug in minus x squared into each one of these. So I have 1 minus x squared plus, I'm squaring it, so now it's the same as x squared over 2 factorial. And then I'm going to have minus, wait, this was x squared. This should be x to the 4th. X to the 4th. And then I'll have, plugging in x squared here, I'll get minus x to the 6th over 3 factorial plus, and now minus x squared is the same as x squared, so I get x squared to the 4th is x to the 8th over 4 factorial minus, and so on. Can you see how the summation notation, I don't know, to me it just seems easier to plug in minus x squared because I only have to plug it into one term. I just have to simplify this to get this, and then I could expand. But this is absolutely fine. You'll get the same thing. Now we want to find the integral of e to the minus x squared dx. So I'm going to just use well, I'll write the integral as a series, and then we'll just use part of it to evaluate between 0 and 1. I just realized I didn't turn the software on that captures this video, and I'm hoping that I only missed one frame and that it was this one. So I'm going to go on from here, and I'll explain this again. Hopefully you saw how we derived the series for e to the minus x squared, and then in this frame I integrated the first 5 terms of it. So if we just take the first 5 terms of this infinite series and integrate, you see, integrating 1, I got x minus 1/3 x cubed, 1 over 5 times 2 factorial, 1 over 7 times 3 factorial, x to the 7th, and so on. So I just integrated the first 5 terms, and I want to evaluate those between 1 and 0. So you can put this on pause and see how I got this minus 0, and using my calculator, 0.7429. Then I didn't write it down, but I went to Mathematica and calculated it. And of course, Mathematica is using numerical methods. I don't know which ones. Mathematica certainly cannot use the fundamental theorem here. But the answer that Mathematica got was less than 0.004 from the one that we get by just integrating the first 5 terms of the power series. Okay, just 2 more examples. Sometimes you're given the series and you are able to find the elementary function represented by the power series. And you'll just be using the table of 5 series. So I don't know, for this I can see it looking at it there, but I think it's better if you just write out part of the series. When k is equal to 1, we get 1 times x to the 0 is 1. And then we're going to have plus, there's no alternating here, 2x plus 3x squared plus 4x cubed plus 5x to the 4th, and so on. Well, looking at those terms, you can see that that is a very clear sum of derivatives. So let's write it as the derivative with respect to x. Where the series converges, we can differentiate and integrate and have the same interval of convergence. And this is just the derivative of x plus x squared plus x cubed plus x to the 4th plus x to the 5th, and so on. And that's our series for 1 over 1 minus x. So this series must be the derivative of 1 over 1 minus x. And differentiating that, we get minus 1 over 1 minus x, the quantity squared, on the interval minus 1, 1. That's the only place that the series, this series, converges to this function, to this graph, only for x between minus 1 and 1. Okay, this is our last example, and the instructions are to try to find an elementary function to which this series converges. And it's just by using the table of functions that we have. So let's see. Let's write it out. So when k is equal to 0, x to the 0 is 1, 1 factorial, so we have 1. And plus, it's not alternating. Then k is equal to 1, and I'm going to get x over 2 factorial plus, and now it'll get easy, x squared over 3 factorial plus x cubed over 4 factorial plus x to the 4th over 5 factorial plus, and so on. Okay, well, if you look at your table, you see this looks an awful lot like e to the x. Let's see, what was e to the x? We know that e to the x was equal to summation x to the n over n factorial from n equals 0 to infinity. In other words, e to the x was 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. That was e to the x. So look at ours up here. What do we want? How could we get this from this? Okay, so this is a little bit tricky here. Let's see. This is e to the x is equal to, now I want to get this in. I see that the 1 I have to kind of leave alone here, but if I just look at this part, if I divided an x out of here, I would have this right here, the whole thing. So I'm going to factor an x out and write this series as 1 plus x over 2 factorial plus x squared over 3 factorial plus x cubed over 4 factorial plus dot dot dot. Okay, now why did I factor that out? Because now I see that this series right here, this or this, is right here. So now let's call that thing g of x, just so I don't have to write out the whole thing. Let's call this converges to, is a power series for some function g of x. It is g of x for some values of x. So let's see, then we have e to the x is equal to 1 plus x g of x, and we want to solve for g of x. Well, you'll get g of x is equal to e to the x minus 1 and then we have to divide by x. So this is the function that this series converges to. And knowing that the series for e to the x, this series here, converges for all x, converges on the entire real line, then this series will too converge on the entire real line. So we have that function, the series converges to it on minus infinity, infinity.